In the next section, we're going to deal with slightly more complicated areas involving multiple functions which are revolved around the x-axis. So in part A of example 3, we've just got to verify that the coordinate of A is 1, 3. This word verify means that you're allowed to accept that that's the answer. You don't need to show how you'd get that answer if you didn't know it. Verify just means make sure that it works. So we basically just got to make sure that 1, 3 is the point of intersection of these two graphs. So we just need to sub in x equals 1 and y equals 3 into both of these graphs and check that they work. So for the line, if we sub in x equals 1, we'll have 5 minus 2x will be equal to 5 minus 2 times 1, which is 3. So that means that 1, 3 is on the line. And similarly for the curve, we'll just sub in x equals 1, so we'll have 1 cubed plus 2, which is 3. So 1, 3 is on the curve. And that's all we need to do. So for part B, we're going to rotate this region R around the x-axis. So now we're going to combine rotating it around the x-axis and the y-axis in one exercise. So you've just got to be careful that you use the correct formula. So let's just write down the formula before we do anything else. The formula will be, because we're revolving around the x-axis, it'll be pi y squared dx. And remember, that's because the radius of each cylinder, when we rotate it around the x-axis, will be the y-coordinate. So you might be able to guess how we're going to rotate this region around the x-axis. We're going to kind of do it in two steps. We're going to split this region, R, into two separate regions, and we're going to rotate the left region around the x-axis and then the right region around the x-axis. So let's draw out our diagram. You don't need to, but I'm just going to draw it out to make it clear what we're doing. So first of all, we're going to take this, the region which is bounded by the curve, the black curve, and rotate that around the x-axis. So we've got this curve that looks something like this. And we've got some portion of the curve which we're going to rotate around the x-axis. So rotate like that. So we know that the limits on the x-axis of this region are 0 up to 1. That's why we did part A, because we know that value there is 1 on the x-axis. And we know the equation of this curve is x cubed plus 2. So we're just going to rotate that around the x-axis first. So the volume of this solid is going to be integral of pi y squared dx, and the limits are going to be from x equals 0 up to x equals 1. So we'll just sub in the value of y. I'm going to take pi outside of the integral, so we'll have x cubed plus 2 squared dx. Okay, so now we can just multiply out the bracket. So we'll have x to the power of 6 plus 4x cubed plus 4 dx. And if we integrate that, we're going to have a 7th x to the power of 7 plus x to the power of 4 plus 4x. And the limits are 1 and 0. And then we'll just sub in our top limit, and we'll get 7th plus 1 plus 4, and then subtract, sub in the lower limit, 0, and we get 0. So we'll have 36 over 7 pi. Okay, so we've rotated that red region on the left around the x-axis. Next, let's rotate this region around the axis. So let's draw a sketch of that again. This time we've got the line, and we know that we're going to start rotating at 1. on the x-axis because that's the x-coordinate of A, and the root of this graph is 5/2. So we're rotating that region around the x-axis. So there's two ways of doing this. One method, which is really the preferred method, is just to realise actually if you rotate a triangle around the x-axis, you're just going to get a cone. So using the fact that it's a cone. So if you imagine the cone, you're going to get a cone that looks something like that, and the radius of the cone is going to be that length there. Let me do it red so you can see it, and that's just going to be the y-coordinate of this point A. So the y-coordinate of A was 3, so the radius of this cone is going to be 3. And obviously the height of the cone is going to be the difference between 1 and 5/2, which is 3/2. So we can use the formula for the area of a cone, volume, is 1/3 pi r squared h. So the radius is 3, and the height of the cone is 3/2. So that's actually equal to 9/2 pi. Another method which is equally valid would be to use the fact we know the equation of this line. The equation of this line is 5 minus 2x, y equals 5 minus 2x, and then you could just use integration. So we'll use the formula, the volume of the revolution is pi integral of y squared dx, and our limits are x equals 1 up to x equals 5/2. So let's sub in y. This time we're using this equation because that's the boundary of our region that we're rotating. It's the line. So it's going to be integral of 5 minus 2x all squared dx between 1 and 5/2. And so we'd have pi, multiply out the double bracket, 25 minus 10x plus 4x squared between 1 and 5/2. Sorry, this should be minus 20x. And I'm not going to go through the whole process, but if you work that out and you checked it, you would get 9/2 pi, which is the same as what we got for the cone. So our final step is we wanted to know what do you get if you rotate this whole blue area around the x-axis. Well, that's just going to be the sum of the two volumes. So the total volume is just going to be 36/7 pi plus 9/2 pi. So we'd get the answer of 135/14 pi.